Okay, so let's do this calculation. So let's see here. You said that we're going to solve for Q, so Q is equal to I times T. So the current is 0.1 amps or 0.1 coulombs per second. Now the time has to be in seconds. So how many seconds are in 30 minutes? Okay, so 30 minutes is 1,800 seconds. Thanks, Daniela. So now we have, let's see, so 0.1 times 1,800 is equal to 180 coulombs. So now we can figure out N. So N is equal to Q divided by F. So that's going to be 180 divided by 96,500 coulombs per mole of electrons. We do this calculation. N is equal to 0.00187 moles of electrons. So once we know the moles of electrons, the next step would be to so for every 1 mole of electrons which pass through the cell, how many moles of silver? Yeah, we have 1 mole of silver, and then from here we want to. Yeah, what's the molar mass of silver?
108.
Pardon?
108.
Okay, 108 grams per mole. So when we do this calculation, .2 grams. Now, electroplating has been around for a long time. Ideally, when a substance is electroplated, you want the coating to be, you want the plating to be uniform, so that's not so easy to do. So I've heard stories in which various substances, various additional substances are added to the plating solution to try to get a uniform plating of that metal onto the spoon. So I've heard of things like these old electroplaters would throw things like shoes and belts and bodily fluids and things like that into the electroplating solution to try to get the coating or the plating of that metal uniformly on the thing they're trying to plate. So I'm not quite sure what's going on there, but that's what they used to do. Rolando.
Why doesn't it?
Well, often because, one reason is because the object they're trying to plate isn't a symmetrical shape. I remember last semester in Chem1A when you were dyeing fabrics with food coloring. So it's sort of the same thing. You want to make sure you have a uniform color of the fabrics. The same thing, you want to make sure you have a uniform coating of that metal onto the substrate plate. So it was almost like some, what they call it, like black magic going on with the plating.
Because I mean, it's got a charge on it, and you're working at the.
Yeah, but I guess one thing too is the charge on the substance you're trying to plate uniform throughout the entire substance, and maybe the answer is probably no.
Because of impurities, or?
Impurities and yeah. Okay, so anyway, you can use these two formulas to figure out how much the mass of a substance plated on the spoon. Now note that you can also change the current and the time, and that's going to change the amount of substance plated on the spoon. Okay, let's move on. As a battery discharges, the voltage drops. So you calculated, and you actually did this experiment in lab either last week or 2 weeks ago. A copper zinc voltaic cell produces 1.1 volts as long as the copper ion solution and the zinc ion solution are 1 molar and the temperature is 25 degrees. So these conditions, 1 molar and 25 degrees, these are standard state conditions for electrochemistry. So as the battery discharges, what happens to the zinc and copper electrodes? Does the zinc electrode get bigger? The copper electrode gets smaller? Or is it the reverse? The copper gets bigger, the zinc gets smaller, or no change? And then what happens to the copper ion solution and the zinc ion solution? The zinc ion concentration increases, the copper ion concentration decreases. The opposite happens, or no change. Okay, so what's happening there? So how would you go about answering these two questions? Would you treat this as a typical multiple choice exam? A question, you know, let's see, eeny, meeny, miny, mo, and whatever you come up with is the answer? Or, what would you do? What would you do to answer that calculations? What kind of calculation would you do? Or what formula would you use? Okay, you actually don't have to do a calculation to answer these two questions. So what observation would you make?
If we were coating the copper penny with zinc, that would suggest that the zinc would be getting smaller and the copper would be getting bigger.
No, but this is a plating experiment. This is where you're making a battery.
Well, still think though, it's the same thing. So the zinc is losing that copper.
And how do you know that the zinc is gaining? Would you say? So you said that the zinc metal is losing electrons, and then you said the copper ion is gaining electrons?
Yes.
Okay, so if we were to draw a picture of the cell, so Juan, you're saying that if you draw a picture of the cell, okay, so here is the zinc, and here's the copper. And here's the salt bridge. And then in this solution we have the zinc ion, and in that solution we have copper ion. Okay, so what reaction is occurring at each electrode?
We have reduction at the zinc.
So you're saying that the zinc ion is being reduced to zinc? Or is it the zinc being oxidized to zinc ion? Okay, now remember, the way to remember is which metal is more active, zinc or copper? Yeah, so zinc is more active, so the more active metal is going to be the one which is, loses electrons, which is oxidized. Okay, so again, the more active metal is the one which is oxidized, so we want to show the reverse of this reaction. So we have zinc going to zinc 2 plus 2 electrons, which means that the copper electrode, what's happening? Yeah, so at the copper, we have copper ion being reduced. Okay, so based on these, on our cell diagram and the half reactions, for question 1, does the zinc get bigger and the copper get smaller, or does the zinc get smaller and the copper get bigger, or no change? So who says it should be number 1? Who says it should be number 2? Who says it should be number 3? Okay, so based on this, note that the zinc is being oxidized to zinc ion, which means that note that the zinc metal should be getting smaller. And note that in this case here, the copper ion is being reduced to copper metal, so that means that this electrode should be getting bigger. So let's see, which one was that? Yes, that should be number 2. Okay, so the zinc should be getting smaller, and copper should be getting bigger. And for the second question, what happens to copper 2 plus ion and zinc 2 plus ion concentrations? So is it number 1, 2, or 3? Who says it's number 1? Who says it's number 2? Who says it's number 3? Okay, so note here that the zinc is being oxidized, the zinc ion, that means the zinc ion concentration is increasing. The copper 2 plus ion concentration should be decreasing because the copper 2 plus is forming copper metal, so the answer should be, let's see, number 1. Okay, so as a zinc copper battery is discharging, we should see the zinc electrode getting bigger. Sorry, the zinc electrode getting smaller, the copper electrode getting bigger, and then the zinc ion concentration increases, the copper ion concentration decreases. Okay, then we just drew our picture of it. So in our discharging battery, note that this electrode is getting smaller. Okay, then this concentration is increasing, and then this is actually getting bigger. Okay, there's more copper being formed there. And then the copper ion concentration, that's decreasing. Then for a dead battery, what happens? What's a dead battery then? Yeah, so when all those reactants have reacted, the voltage for a dead battery is going to equal zero. Now we can actually do a calculation to figure out the voltage as the battery discharges. So to do that, we use the Nernst equation. So this is the Nernst equation. E cell or the battery voltage equals E cell under standard state conditions minus RT over NF. R is the gas constant, 8.31 joules per mole per degree. T is the temperature in degrees Kelvin. N is the number of moles of electrons transferred. F is Faraday's constant times the natural log of the products divided by the reactants. Okay, so let's do this calculation. Calculate the cell voltage when 10% of the reactants have been consumed. So we're looking at that zinc copper battery. So under standard state conditions, let's say that the initial concentration is 1 molar for the copper ion and zinc ion concentration. Note that when 10% reacts, that means 0.1 molar has reacted. So note that in this case here we have 0.1 molar of the copper ion has reacted, which means that 0.1 molar of the zinc ion has been produced. So the amount which is left over is 0.9 for the copper ion, 1.1 for the zinc ion. So let's plug that into this Nernst equation and figure out what the cell voltage is going to be. Okay, so we have E cell. Now, what's going to be E cell under standard state conditions for the zinc copper battery? Okay, so what's E cell going to be for that zinc copper battery? Yeah, so in the previous slide we said that that voltage should be 1.1 volts. Okay, so we can figure that out by looking at table 19.1. So the gas constant R is 8.31 joules per mole per degree Kelvin. Let's say the temperature is 25 degrees Celsius, so 298 Kelvin. How many electrons are transferred in this zinc copper battery? Yeah, so looking at here, we have 2 electrons transferred. Okay, so 2 electrons are transferred from the, let's see, from the copper to the zinc. So we have 2 electrons here. The Faraday's constant is 96,500 coulombs per mole. And then we have the natural log. Now, this is like looking at an equilibrium constant. So when we look at our overall reaction, we have zinc plus copper 2 plus going to zinc 2 plus copper. So if we look at an equilibrium constant KEQ, what would that equilibrium constant look like for this reaction? So that's going to be equal to the concentration of zinc. So our product, which is zinc 2 plus, divided by copper 2 plus. And remember that for a pure substance like copper metal and zinc metal, that concentration we set equal to 1. Okay, so for this case here, this is going to be zinc ion divided by